Welcome to this video lesson. In this video, we will be doing a couple of examples with questions involving force of friction. All right, in our first example, we have a situation in which in an investigation, a student places a 1.2 kilogram card on a table. They tie one end of a light string to the front of the cart, run the string over a pulley, so we get it, and let's call that a frictionless pulley, and then tie the other end to a 0.6 kilogram hanging object. The coefficient of kinetic friction between the cart and the table is 0.16. Determine the magnitude of the acceleration of the cart and the hanging object. Calculate the magnitude of the tension in the string, and what coefficient of static friction is required to prevent the cart from moving. Let's start with the first part of the question. We've talked about solving these types of questions before. Usually the method that I choose is I determine the direction of acceleration, and any forces that are acting in the direction of acceleration, I'm going to label them as the positive x direction, and anything that goes perpendicular to this is going to be my vertical direction. So this is x and y, and again, x direction is parallel to the acceleration, meaning forces acting in this direction for the cart and this direction for the mass, and anything that's perpendicular to my acceleration, so meaning this direction for the cart and perpendicular this way for the mass, will be in the y direction. And my system is going to be all of this. And let's get started. So looking at my system, there is a contact force here on the cart. This will cause two possible forces, a normal force and a frictional force. In this question, friction is not negligible, so we know that we have a force of friction. So I'm going to draw that first. So I'm going to choose my system to be the cart and the mass. Instead of mass, let's just label this A, and let's call this C for cart. The surface here I'm going to call W. And I'm just going to change this to A. I think it's a little bit better than just mass. Okay, so I got my system. The two possible forces acting from the surface, one is normal force acting upwards, that is perpendicular, therefore it is going to be a vertical force. That's the normal force acting from the surface, W, onto C. And there's going to be a force of friction. Since we're going to make an assumption that this is going to be pulled in this direction, force of friction is going to go opposite to it. That force of friction is parallel to the x direction, or the acceleration, and therefore I'm going to be drawing it in the x direction. This is the force of friction caused from the surface W onto C. All right, there is also a gravitational force acting on this object, and that's acting towards the Earth, and since that is perpendicular to my acceleration, I'm going to be drawing it in the vertical direction, and that's going to be the force of gravity acting on from Earth onto my cart. So I've now taken care of the gravitational force acting on this. I've taken care of the surface here. These two forces are those. There's also an attachment here on my cart, but that's inside of my box, and anything inside of the box will be an internal force, and force diagrams only consider external forces. Now let's look at my other objects inside. I see this object over here, and there are two forces acting on this, gravitational force and the tension force. The tension force is going to be considered as an internal force. So the only force is that I need to consider for my system here will be the gravitational force acting on the mass here. That force is acting downwards, and that's parallel to my acceleration. And anything that's parallel to my acceleration, I will be drawing in the x direction. Since it's going down and in the same direction as my acceleration, I'm going to draw it in the positive x direction. We are thinking that this is going to accelerate, so I'm going to draw this force slightly bigger, and this is going to be the gravitational force acting on A. The direction of acceleration, I will draw it here with a squiggly, and I have my system diagram. Oh, sorry, I have my force diagram here for systems C and A. To determine the acceleration, I'm going to use the net force equation, and I will need to write this out as the sum of forces. This is the gravitational force acting on A plus the force of friction acting from surface W onto C, and that's going to equal to mass of my system. Mass of my system here is going to be mass of C plus mass of A multiplied by the acceleration in the x direction. Let's see if we have all the information we need to solve this question. Force of gravity for A, we have its mass and gravitational acceleration is 9.81, so we have all the information here. Force of friction from W to C, we don't have that one, but we have enough information that we can use to calculate it, so we'll think about that in a second. And we have these two masses, and we need the acceleration. So we do need to find the force of friction acting on our cart here. Well, in order to figure out that force of friction, I would have to think about the cart on its own for a second and look at what forces are acting on it. So I'll do that separately here. And there's a normal force acting from W to C. There is a force of, or gravitational force acting on C. There is the tension force acting on, sorry, from A to C, and there's force of friction acting from W to C. This force of friction will be the normal force acting on the cart multiplied by the coefficient of friction. In this case, for the normal force, I have to make sure that I can calculate it using gravitational force. I can see that the only forces acting vertically on my cart are these two forces. And since this is not accelerating up or down, these forces need to balance each other out. And therefore, the magnitude of Fn is equal to magnitude of Fg. So I will write that here. Since acceleration in the y direction equals to 0, therefore the magnitude of Fn Wc is equal to the gravitational force C, and that's because they need to balance each other out. So force of friction from W to C will equal to the normal force W to C multiplied by mu. The normal force is equal to the gravitational force acting on C, and this is equal to, I'll just write it down, mass of C times G. So this is going to equal to mass of C times G times mu. My mass is 1.2, gravitational acceleration is 9.81, and my mu is 0.16. And when I plug all of those into my calculator, I will get 1.88353 Newton for my force of friction. I'm going to go back and plug all my values into this equation. So we have the force of gravity actually, I'm going to turn them into magnitudes before I go ahead and plug in the values. So this vector over here, I'm going to take right to be positive just so that it's aligned with my acceleration. This force over here, it's moving in the right, that's positive, so I'm going to call this FGA. This force over here, it's acting in the opposite direction of my positive, so I'm going to use a negative force of friction W to C is going to equal to mass C plus mass A, and my acceleration is acting to the right, and my positive is to the right, so I will use a positive. Now everything is turned into magnitudes. I can go ahead and plug in all the information. For force of gravitation for A, that's going to equal to mass of A multiplied by G minus the force of friction. I'll plug in the value, 8. I'll use the exact value on my calculator. MC's value is 1.2, MA is 0.6 times the acceleration. Mass A is 0.6 multiplied by 9.81 minus 1.88 is going to equal to 1.8 times AX. I will do this on my calculator. 0.6 times 9.81 minus the exact value there, 1.88, will equal to 4.00248. And this is going to equal to 1.8 AX. Divide both sides by 1.8, and I will get 2.2236. And I just want the magnitude of acceleration. So this is going to be approximately, I need two significant figures, 2.2 meters per second squared. And I will highlight my answer. All right, so that was it for finding the acceleration. Now, we want to also find the magnitude of the tension on the string, and we can use either the cart to do that, or we can use the mass here. It's really up to you which one you're going to choose. In this case, for the cart, I have one force, one force, yeah, and two forces. And for this one, I also have one force and two force acting on it. So, and I've already calculated the force of friction acting on this, so it really doesn't matter. I'm going to choose, I'm just going to move things a little bit to this side over here. And I've already drawn a force diagram for this in order to figure out the force of friction on it, so why not use this system. So for part B of my question, I'm going to take right to be positive because I know that the acceleration is in this direction, and F net x is going to equal to the sum of forces. In this case, it's force of tension plus the force of friction, and that's going to equal to mass of the cart multiplied by its acceleration. I'm going to turn everything into magnitudes. So this force is acting to the right. That's positive. I'll write it here just for more space. Force of tension AC. This force is going to the left. My positive is to the right. I'm going to use a negative. And this is force of friction, W to C. That's going to equal to mass of C multiplied by the acceleration. And the acceleration is also going to the right, and that's positive, so I will use a positive there. I'm trying to find the tension force, so that's FTAC minus force of friction. Calculated that right here. So that's going to be 1.88. That's going to equal to mass of C, which is 1.2, multiplied by the acceleration, which I have found as 2.2236. I will plug this into my calculator. And once I add 1.88 to both sides, I will get 4.55184 newtons. And if I want to represent that using proper number of significant figures, I'm going to go with 2 significant figures, and that's going to be 4.6 newtons. And I will highlight my answer. Perfect. I have found my answer for part B. Let's zoom out a little bit, and I'm going to make sure that this is parts. I'm going to label part A as well so we can see that. This is part A. And now I have to do part C. What is the coefficient of what coefficient of static friction is required to prevent the cart from moving? Okay, so we're trying to figure out what would be the static coefficient of friction here, or the minimum value for it anyways, that would prevent the cart from moving. So in this case, the coefficient of friction is no longer 0.6. That means that we don't have that. I have my force diagram from my system, so I'm going to use the same force diagram here. And this is for part C, and I'll write it here. I'm going to take right to be positive, doesn't really matter. And F net X is going to equal to the sum of forces, FGA plus force of friction from the surface onto C, and that's going to equal to mass of my system, which is mass of C plus mass of A times the acceleration. The acceleration is 0 when my object is not moving. So this whole term becomes 0, and it makes my life a lot easier. For gravitational force on A, that's going to equal to mass of A multiplied by G. It's acting to the right, so I'll use positive. Force of friction, it's acting to the left, so I'm going to use negative. In terms of its value though, it's going to be, we know that force of gravity is going to be the normal force acting on it multiplied by mu. We don't know the mu here, so I will not, so I'll just put it as mass of C multiplied by the gravitational acceleration multiplied by mu. This is static. And I'm taking this, I'm just going to highlight it so that you can see and refer back to it whenever you need to. Basically, I took this from the fact that force of friction from W to C's magnitude is equal to mass of C multiplied by the gravitational acceleration multiplied by mu. In the last section, this was the kinetic because it was moving. Now it's the static one. This is going to equal to 0. So now I have, let's see if I can find my information. I have mass A, I have G, I have MC, I have G, so I just need mu. And I can do that. It's not a problem. Mass of A, 0.6, gravitational acceleration, 9.81, minus mass of C, 1.2, gravitational acceleration, 9.81. You could have factored that out, would have made your life a lot easier. Multiplied by mu s is equal to 0. And I'm going to do this on my calculator. And I should get, I believe, 0.5. And for 2 significant figures, it will become 0.50, my final answer. I'll just show you quickly how you could do this with factoring it out. so that you can see an alternative method of solving this algebraically. Here I could have factored out the g, and I would have ma minus mc mu s is equal to 0. Divide both sides by g, and I would get ma minus mc mu s is equal to 0. Rearrange for mu s, and I would have gotten ma over mc, and if I plugged in the values, I would have gotten 0.5, approximately 0.50 to two significant figures. So again, different methods of doing it, and they would yield the exact same answer. All right, this is fantastic. So we know if the static coefficient of friction was 0.5 or anything higher than 0.5, then our object will not move. It will stay stationary. If anything less than 0.5, then it will start to accelerate. And basically in this question, it was 0.16, and we saw that for 0.16, our objects do accelerate. All right, let's do another example. All right, we got Luigi, who has tied up two mushrooms together and using a rope to pull them across ice with force of 200 newtons. So this force over here is going to be 200 newton. To the right, the mass of the first mushroom is 20 kilograms. So let's write those information down. So this force is 200 newtons. Mass here is 20, mass here is 15. The coefficient of kinetic friction for each, I should say mushroom, I don't know how it became a sled, mushroom is 0.2 relative to the floor or the ground or the surface. Good. So mu is equal to 0.2. Draw a free body diagram using both mushrooms as your system. So this is part A. I'll do part A over here. I just want to have the proper spacing. Okay, this is my system. There's force of gravity acting on it. So this is the gravitational force acting. Let's call this mushroom A and this one B. So this is A, B. And I know that my mushrooms, if they were to accelerate, they would be accelerating in this direction. So I'm going to call this direction X and this direction Y. And note that I always draw the forces that are acting in the direction of acceleration in the X and direction perpendicular to that in the Y direction. So force of gravity is downwards, so that's in the Y direction. There's a normal force acting in the upward direction, and that normal force acts both on both of my objects here. So that's the normal force acting from, let's call our surface here W, and that's W to A and B. Okay, good. And there's going to be force of friction acting from surface W onto A and B. And there is going to be a force from Luigi, and that force is going to equal to 200 newtons. And this is my force diagram here. Next, we have to calculate the acceleration of the mushrooms. So let's do that. I'm going to write the net force equation in the x direction. That equals the sum of forces. This is AB. And that's going to equal to the mass. I should say what my system here is on my question. So my system is A and B. So it's going to equal to mass of A plus mass of B multiplied by the acceleration in the x direction. Now so you can do this in many different ways. I'm just going to enter the values right now. I'm going to take right to be positive, align it with the direction of acceleration. So that would mean that since this force is acting to the right, I'm going to use a positive value for it. So I will turn them into magnitudes right away. Force of friction in this direction is opposite to my positive, so I'm going to use the negative for it. I don't have the force of friction value, so I'm just going to write it as force of friction W to AB, and that's going to equal to the sum of the two masses. In this case, the two masses is, I'll just write it as MA plus MB times AX. We can see the acceleration is to the right and right is positive, so I will turn that into a positive A. And once I have this, my value of force is 200. I don't have force of friction, and that's going to equal to the mass A plus mass B. That's 20 plus 15 times the acceleration. So what I need here is the force of friction. In order to find the force of friction, I will have to multiply the normal force by the coefficient of friction. And the normal force here, in this situation, because my object is not accelerating upwards, these two forces need to be balanced and they need to equal. So I'll write that here. So acceleration in the y direction is equal to 0. And therefore the normal force acting from the surface onto AB is equal to the gravitational force acting from on A and B. And again, you can see that I'm using magnitudes here because that would mean that these two forces need to be balanced. So the magnitude of this force and the magnitude of this force is the same. I do want you folks to write this line down and not just say that this is the case, because and sometimes it's not the case, and I need to make sure as physicists you know why it is that this is equal to this. All right, so now that we have this, we know that this is going to equal to force of gravity acting on A and B, so that's going to be mass of A times gravitational acceleration plus mass of B times gravitational acceleration. Let's do this on our calculators. We will have 20 times 9.81 plus 15 times 9.81. And we will get 343.35. And to find the force of friction from the surface onto AB, we will multiply mu by, or kinetic mu, by the force of normal, and that would mean it's 0.2 multiplied by 343.35, which will equal to 68.67. So now I can go and use this value in here. This is 200 minus 68.67, and that's going to equal to 35 times A. Using my calculator, I get 131.33 is equal to 35 AX, and that AX is equal to 3.7522, and approximately to guess three significant figures here, 3.75 meters per second squared. And I guess we need the direction for this one because it's asking for acceleration and not magnitude of acceleration. And that's going to the right. And I can highlight my answer. I now just noticed that I completely forgot part A of this question, and this is part B, and this is part C, but that's okay. And now we need to determine the magnitude of the tension of the rope between the sleds. And we can definitely do that. We need a force diagram for one of these, either this or this. In both cases, they both have force of friction acting on them. They have a tension force. And this one has an extra 200 force in this direction. So I'm actually going to use mass B for my force diagram because it only has in the x direction only this force and force of friction. And I guess this will also answer part of part A. All right, I am going to move this down and I'll work right here. I just need the acceleration value. I'm going to use my system, or sorry, this is part D, I believe now. For my system, I am going to use mushroom A, mushroom B, and the forces acting on this mushroom is the tension force acting from A to B. And we got force of friction. And this force of friction is acting from surface W onto my mushroom B only. There is going to be a normal force acting from the surface onto my mushroom B. And there's going to be a gravitational force acting from my surface, acting from Earth onto my mushroom B. Okay, first let's find the force of friction acting on my mushroom, and then I will use that to find everything else. So to find force of friction, I know that force of friction, W to B, is going to equal to mu times the normal force. And I'm just finding the magnitude here. I don't need the direction. So in terms of magnitude, this is the equation. The normal force acting here is going to, in terms of magnitude, is going to equal to the gravitational force since acceleration is 0. So I can just write since acceleration in the y direction is equal to 0. Therefore, this is going to equal to mu, and this force over here, which is the normal force, is going to equal to the force of gravity acting on B. No problem so far. This is going to be mu, and force of gravity acting on my mushroom B is going to be its mass times gravitational acceleration. I can just put the numbers in and find the force of friction right away, or I can just use the expression. I'm going to leave it as the expression in this so that I can show you how that works. Okay, so I am now going to write F net x, and this is going to equal to the sum of forces. I'm going to take this to be right, and my forces acting in the direction of acceleration are the tension force and the force of friction. And that's going to equal to mass of my system, which is mass B multiplied by the acceleration. I'm going to turn them into magnitude. This force is to the right. Right is positive, so I'm going to use a positive. This force over here is going to the left. This is positive is to the right, so therefore I'm going to use a negative. And Mass B is just mass B. It's not a vector quantity. AX is going to the right. Positive is right, so I'm going to use a positive. Once I have all of this, I need the tension force minus, instead of force of friction, W to B, I found the expression for it right here. So I can just plug it in as mu MBG, and that's going to equal to MBAX. Now I have all the information that I need. I have mu, I have mass B, G, mass B, and the acceleration's magnitude. So everything is ready to go. I can solve this by adding this to both sides first and then plugging in the value. I can do it just by plugging in the values right away. So let's just plug in the values. 0.2 was the coefficient of kinetic friction. Mass B was 15. Gravitational acceleration is 9.81. That's going to equal to mass B, which is 15, and the acceleration is 3.7522. And I'm going to use the exact value when I'm doing my calculation. Once I put all the values on my calculator, I will get that the tension force acting between A and B, its magnitude is going to equal to 85.7 approximately newtons. And I just need the magnitude and no directions here. And this is going to be my final answer. All right, the last part of this question says, how would the acceleration change if the coefficient of friction between the mushroom and ice was larger? Well, let's kind of look at this and I'll explain it. We have the force of 200 Newton is acting in this direction. As soon as the coefficient of friction here is increased, the total force of friction acting on the two mushrooms also increases. If that's the case, that would mean that the net force acting on the two mushrooms will also decrease. So again, this is 200. At the moment, force of friction is 68. If, let's say, coefficient of friction increased, let's say the force of friction increases from 68 to 100, that would mean that the net force is reduced to 100 instead of 131. And if that's the case, if the net force is smaller, that would mean that the acceleration is also reduced based on second law of motion, because based on the second law of motion, the net force is equal to, or the simplified version of second law of motion, the net force is equal to mass times acceleration. And if the net force is smaller, but the mass is the same, that would mean that the acceleration is reduced. And here we go, 2 examples on force of friction. I hope that they are helpful for you. I hope that you have a wonderful day.